Swayam Prabha. Digital India. Educated India.
Good morning. In the previous lecture, we studied one of the four methods to work out suitable similarity transformations for solving the eigenvalue problem, that was through plane rotations. Today, in this lecture, we consider the second method to work out suitable similarity transformation. This is also related to geometrical ideas, and this particular method is based on reflection. So, today we will study Householder transformation and tridiagonal matrices. First, we consider the Householder reflection transformation in a geometric sense, and then we work out how to find the Householder method for tridiagonalizing a given symmetric matrix, and next we see what to do with that resulting tridiagonal matrix, symmetric tridiagonal matrix. So, first consider this. In a k dimensional space, consider two vectors u and v in this k dimensional space, both having the same magnitude. If u and v have the same magnitude like this, then we proceed to find this particular vector w, which is the unit vector along the direction of difference of u and v. That is, u is this, v is this. This vector is the difference u minus v, and we divide it with its magnitude to find the unit vector w in this direction. Now, this small vector w, unit vector in this direction, is perpendicular or orthogonal to this plane or hyperplane that actually bisects the angle between these two rays, showing the two vectors. Now, with this w in hand, let us construct this matrix Hk, which is a k by k matrix formed by subtracting the matrix twice w transpose from the identity matrix. This matrix is called the Householder reflection matrix. This has a lot of interesting properties. This is a matrix which is symmetric and orthogonal at the same time. Symmetry is easy to see here, because identity is anyway symmetric and w transpose is symmetric. So, this difference is symmetric. To check for orthogonality, we can find out whether Hk transpose Hk is identity. To see that is actually quite simple. Hk transpose Hk, and symmetry we have already confirmed, we have already verified. So, in place of Hk transpose Hk, we can simply write Hk. So, Hk into Hk, right, identity minus twice w transpose into the same thing. As we open this product, we get I into I, that is identity, minus I into twice w transpose, and again twice w transpose into identity. So, total 4 w transpose, minus minus plus 2 into 2 4, and we get w transpose w transpose. Since matrix multiplication is associative, so whichever order you multiply these 4, it does not matter. So, if you multiply in this first, then you will find that w transpose w is unity, because w is a unit vector. Then what remains? 4 w transpose, which is the same as this. So, that will mean that HK transpose HK is identity. That establishes the orthogonality of this Householder reflection matrix. Now, what does this symmetric and orthogonal matrix do? Why it is called reflection matrix? To see that, consider its action on two vectors, one along W and the other perpendicular to W or orthogonal to W. Orthogonal to W will mean a vector in this plane, which is shown here as plane of reflection. So, take any vector x which is orthogonal to W, that means which is in this plane. So, when you apply HK on x, you find that IK minus twice WW transpose x, what you will get? Identity into x is x, and this one as you open you will find first W transpose x, and from the very definition of x being orthogonal to W, W transpose x will be 0. So, what will remain? Identity into x which is x. That means a vector orthogonal to W, that is in the plane of reflection, gets mapped to that same vector itself. There is no change. On the other hand, how does W itself get mapped? HKW, as you apply this on W, you find that identity into W will give you W, but this fellow will give you twice W. W transpose W is 1. So, you will get W minus twice W, that is minus W. That means W itself, when operated upon by HK, gets mapped to its negative, and the vector in the plane of reflection gets mapped to itself. That is the way a reflection takes place. This plane of reflection operates like a mirror, right. So, if there is any other vector which has some component on the plane and some component perpendicular to it, then we can consider it like this. Applying HK over y, which has two components, along W which is perpendicular to the plane and perpendicular to W which is along the plane. The component which is along W gets mapped to its negative, and the perpendicular one remains as it is, right. So, this is typically the action of a mirror reflection. So, this is why this matrix is called a Householder reflection matrix. In particular, it will map U to V and V to U, because they are mirror images of each other with this plane as the mirror or plane of reflection. Now, this concept and this particular matrix, how do we utilize in reducing the symmetric matrix to a form more suitable for solution of the eigenvalue problem? In this case, we will try to make it tridiagonal. How do we use that? So, that brings us to the point of Householder method. Consider an n by n symmetric matrix and so on, right. Symmetry is shown here, A to 1, A to 1 and so on. Now, take U in that context, in the reflection context, take this U to be the vector A to 1 to A n 1. This transpose makes this row vector a column vector through transposition. Now, if the matrix is n by n, then this vector U is an n minus 1 dimensional vector, because the top entry A11 we have left out, and that vector U starts from A21. That means this vector, this much is taken as U, okay. And then V is taken to be a vector of the same dimension, but it is having a first entry which is the same as norm of U. So, whatever is the norm of this, that turns out to be the first entry of V, all other entries of V are 0. That means, the top entry of V will be the norm of this vector from A21 to A n1, and all the other n minus 2 entries of V will be 0. So, like that we construct the vector V. With this U and V, we work out W, U minus V divided by its magnitude, and then we work out the householder matrix. That householder matrix Hk, in this case k is n minus 1. So, it will be an n minus 1 by n minus 1 matrix, H n minus 1 we call it, right. Then out of that H n minus 1, which is an n minus 1 by n minus 1 matrix, we develop this larger matrix by inserting a 1 here, a 0 row above and 0 column on the left of this H. Okay. So, this is P 1. Now, P 1 is its own transpose because it is symmetric and it is orthogonal also. So, then what we do is that we apply this orthogonal similarity transformation, P 1 transpose A P 1, since P 1 transpose is same as P 1. So, we have just written P 1. Now, what we have here is A 1 1 sitting here, U is this whole thing is U transpose, and this much the trailing n by n minus 1 by n minus 1 matrix. For that we give a name, call it A 1, whatever it is. Then as we apply this P 1 A P 1 through the multiplications, you will find that this U has become, in place of U, you have got V now, and in place of U transpose you have got V transpose. This multiplication you can see immediately, we have got P one 0, right. So, 0 row, 0 column and H n plus 1, n minus 1 here, then A, which has A 1 1, U on this side, U transpose on this side, and A 1 here, and again the same P. Now, as you conduct the block operations in eigenvalue problem solution methodologies, you will quite often come across these block operations. So, first keep this as it is, and we multiply these two, A 1 1 scalar into 1 plus U transpose row vector into 0 column vector, that is 0. So, you get A 1 1. Next A 1 1 into 0 row, you get a 0 row plus U transpose into this. What is U transpose into this? That will be the transpose of this, right. So, U transpose into this will be the transpose of this, right. And what is this? This matrix is its own transpose. So, this is simply H n minus 1 U, and through the property of the householder reflection matrix that we have seen just now, this is nothing but V. So, therefore, U transpose this will be V transpose. So, you get V transpose here. Next, the lower row block, U column vector into 1, that gives you U only, plus A 1 into 0, that is 0. So, you get U. Finally, this big block, this is a scalar, this is a row vector, this is a column vector. Now, we have got the trailing n minus 1 by n minus 1 matrix here, column vector U into row vector 0, that is a 0 matrix, plus A 1 into H, we write it. Finally, this multiplication, 1 into A 1 scalar A 1 plus 0 row into U column, that is 0. So, you get A 1 1, A 1 1. Next, 1 into V transpose, row vector V transpose plus 0 into whatever. So, you get V transpose here. 0 into A 1 1, that is 0, that is a column vector, plus H n minus 1 U, that is V. So, you get V here, and here you will get 0 into V transpose, that is 0, plus H into A1 into H, right. So, what you have got? You have got in the first column you have got A11 and then the vector V. Similarly, in the first row you have got A11 and then V transpose. And what is the structure of V that we started with? First entry of V is full size of U and all the other entries of V are 0. That means, below the second entry from the top everything else will be 0. So, that is what you get here, right. So, now we rename. Okay. See, in the whole process A11 has remained unchanged, A11 has not been operated upon by anything, because the first column and first row of P1 is same as identity. So, A11 has been left unchanged. Now, we rename A11 as D1 and whatever is the first entry of V we name it as E2, below which everything else is 0, and out of symmetry that same E2 will be sitting here, on the right of which there will be all zeros, and this 2 2 diagonal entry we now call D2. In the next step this block will remain unchanged. The way in the first step this remained unchanged A11, in the second step this much will remain unchanged. What we do in the second step? In the first column below the top 2 entries everything else has become 0. Next round in the second column below the top 3 entries we want to make everything 0. This is the process to make it tridiagonal. Okay. So, what we consider is that below the 2 top entries whatever is the vector sitting we call that U2, and then construct a similar V2 which has the same magnitude as U2 and all but the first entry, all the other entries are 0, right, and that size of the matrix vector U2 and V2 is n minus 2. Then we construct the next householder transformation matrix of size n minus 2 by n minus 2 and enhance it with an identity matrix of size 2 by 2 here, equivalent number of zeros here and here to complete the size. Then apply that on the previous result this, and this will keep unchanged the leading 2 by 2 block of A1, okay, and you will get the next step which will have this much D1, D2, D3, E2, E3 in the place correct places, and the first 2 columns and the first 2 rows have been made processed up to the extent that below the subdiagonal and above the superdiagonal we have got zeros in those first 2 columns and rows. Like that we keep on conducting steps with smaller and smaller householder matrices in the trailing part, and the leading part we will have the identity matrices of gradually increasing size. After j such steps till this point it has been converted to tridiagonal and remaining fellows are full, and as we go on conducting this these kind of steps, at the end of n minus 2 steps we will have this complete transformation P1 to Pn minus 2 which will result in a completely symmetric tridiagonal matrix, right, which will look like this. Let us see a quick example. Okay. This is a 5 by 5 matrix. Now, this part is what we called A1 there. Now, in order to reduce it to a symmetric tridiagonal form, we would like to have first 3 zeros in these locations, right. So, we take U as this vector 4 1 2 1 and we want V in which the last 3 entries are 0. And what is the first entry? First entry is the size of this vector u. So, what is that size? This square plus this square plus this square plus this square. So, we will have 16, 17, 18 and 4, 22. So, root 22. So, this will become our v, and with this u and this v, it is easy to find out w, the difference of u and v, and divided by whatever is its magnitude, right. So, with that we find w, and then we work out twice w w transpose, subtract it from identity, and that matrix is our 4 by 4 Householder transformation matrix. That 4 by 4 matrix will be sitting here, let us call it H4, zeros here, zeros here. When this matrix is multiplied on this side and this side to this matrix, then the transformation that will take place will make these root 22 0 0 0, similarly here root 22 0 0 0, right. Then we will find that this much is secure, and then whatever is here, this 3-dimensional vector will be then taken as the next u, and the next v will be taken as something 0 0, that something will be the size of this, and then through the similar process in which the Householder transformation matrix in this case will be I2 H3 0 0. This 0 matrix is of size 3 by 2, this is of size 2 by 3, and so on. When this is multiplied on this side as well as on this side, you will get something here, zeros here. The third step here will make this as 0, and whatever happens on this side will happen on this side also. So, you get a symmetric tridiagonal matrix like this. Now, the question is that after we have reduced the matrix to this symmetric tridiagonal form, what do we do with it? That is the solution of the eigenvalue problem of a symmetric tridiagonal matrix anyway simpler compared to the original symmetric matrix? The answer is yes. There are several ways one can handle this kind of symmetric tridiagonal matrices. One way we consider now, and the other way we will consider in the next lecture. There is a very interesting piece of theory which tells you how to work out the characteristic polynomials of submatrices of this, that is leading 1 by 1 submatrix, leading 2 by 2 submatrix, leading 3 by 3 submatrix, and form a sequence out of these characteristic polynomials, and then try to solve the eigenvalue problem based on those interesting properties. So, what will be the characteristic polynomial of this? So, for that we have to find out the determinant of lambda I minus t. So, this is the characteristic polynomial, right, lambda minus d1, lambda minus d2 etc., sitting in the diagonal places, and minus e2, minus e3 etc., sitting in the off diagonal places. Note that d is indexed from 1 to n, and e, the subdiagonal and superdiagonal entries, which is 1 less in number, they are indexed starting from 2. Okay. It could have been indexed as e1 to en minus 1, that would be equivalent to this, but in this analysis we have indexed it from e2 to en. So, there is nothing called e1 in this analysis. Fine. So, with this characteristic polynomial, you find that the characteristic polynomial of this leading 1 by 1 part is simply lambda minus d1, right. So, we call it p1 of lambda, that is the characteristic polynomial of the leading 1 by 1 submatrix from T. So, we call it P1, that is simply lambda minus D1. Right. Then for the leading 2 by 2 submatrix, we have got the characteristic polynomial from here, lambda minus D2 into lambda minus D1 minus E2 square. In this place, lambda minus D1, can we simply put P1 of lambda? We can. So we write this. Okay. Similarly, we can work out P3, P4, etc. But let us go one large step and try to determine Pk plus 1 lambda in terms of Pk lambda and Pk minus 1 lambda. So, that will establish a recursion among all these characteristic polynomials of the leading submatrices. So, as we try to do that, let us write down here we are going to write down here the same matrix that is appearing there, but not up to all the way to lambda minus Dn, but up to lambda minus Dk plus 1. When you try to expand this determinant from this column, what do we find? We find it is lambda minus dk plus 1 into this determinant minus this thing into the determinant that we will find by crossing out this row and this column. So, let us do that, and all other entries are zeros, right. So, we get lambda minus dk plus 1 into this determinant, which is same as the characteristic polynomial of the submatrix one order less, that is lambda minus dk plus 1 into pk, lambda minus dk plus 1 into pk. Then plus this thing, which is minus ek plus 1, minus ek plus 1 into something. We try to find out that something. What will be that something? That something will be the determinant found by removing this row and this column. So, let us do that. Remaining thing will no longer be this. So, we will be removing this column and this row. This determinant should be sitting here, and see its diagonal entries are lambda minus d1, lambda minus d2, lambda minus d3, etc., up to lambda minus dk minus 1, and then next, because this guy has taken this place actually after removal of this row, and in this row other than this entry everything else is 0. So, that means the determinant that we are asking for is this into this determinant, right, and this is minus E k plus 1, which okay, earlier that minus sign, that plus we have not made it plus. So, that minus will actually now help, and because this minus, this remains minus finally, and E k plus 1 comes once more. So, it is square now, and what else is here, that is P k minus 1, that is the characteristic polynomial of the submatrix of one further order less. Okay. And now what we do further other than this, now this relationship, this recursive relationship will define up to P n in terms of the older ones. So, P 3 will get defined in terms of these two, P 4 will get defined in terms of P 2 and P 3 and so on through this relationship. At the top we also put a dummy element in this sequence in order to complete the sequence, and that is 1. Okay. So, then we will say this will have 0 roots, no roots, this will have 1 root which is D1, this will have 2 roots which is, we can find out what are those 2 roots, and so on. So, finally, P n will have n roots. As we construct this sequence, then this sequence has some interesting properties. These expressions, or rather this expression, this recursive expression which is here, helps us in evaluating these polynomials extremely fast. Other than that, this sequence of these polynomials of increasing degree has further properties. They, in particular, they have the property called a Sturmian sequence property. That property they have if all the Ej's, all the subdiagonal and superdiagonal entries are non-zero. Okay. In that case, this sequence P0, P1, P2, all these polynomials, the sequence of all these polynomials has an interesting property. Now, our rest of the process will directly depend on that property, but before that we need to ascertain what we should do if there is some Ej which is 0. Then that is actually for some j, say Ej is 0, some of the subdiagonal and superdiagonal entries turns out to be 0. That is actually a good news, because in that case we can split the matrix. We have D1, D2, etc. up to Dn, we have E2, E3, etc. up to En. Now, if there is a other things are already zeros, if there is some E which is 0 here as well as here, then this is actually going to obstruct us from using this succeeding formulation for the complete matrix, but these two zeros will actually help us in splitting the matrix into two parts, because then we will have the complete matrix in the form of a block diagonal matrix with these two zeros sitting here. Earlier, if we had these as non-zero, then it was such a huge long matrix, okay, large matrix n by n. Now, these two zeros here will decouple the two subspaces completely, and we will actually have this as a block diagonal matrix. This is one block and this is another block. So, whenever we have Ej equal to 0, at that location we can always split the matrix into smaller blocks such that we can consider each block separately. So, having some Ej as 0 helps us in splitting the matrix into small matrices until each such block has non-zero Ej's all through, right. So, we can consider only those cases which have non-zero entries here, for which the rest of the theory holds. Now, what is that particular property? The Sturmian sequence property says that roots of pk plus 1 interlace roots of pk. What is that? That means if you have roots of pk sitting at locations 1, 5, 7, 9, then pk plus 1 say 1, 5, 7, 9. If these are the roots of pk, then the next one pk plus 1 which has one more root, that is 5 roots, say p4 has these as roots, p5 which has 5 roots will certainly have one root below 1, another root between these two, another root between these two, another root between these two, and the fifth root above 9. That means the roots of pk plus 1 will interlace the roots of pk, which in turn will interlace roots of pk3, p3, pk minus 1, and so on, right. So, this is the interlacing property which is shown mathematically like this, and this property leads to a convenient procedure for finding the eigenvalues. Now, I will skip the proof of this particular property, but I will just give you the line of proof and strongly advise you that in the textbook you go through the proof in the textbook or in these slides which are available in the internet. You should go through the proof quite carefully, because the proof has a has an inherent beauty in it. So, the line of the proof is as follows. First, we consider the case of k equal to 1, that is the statement true for k equal to 1, and that is trivially true, because there is only one root and nothing is there to interlace. In the case of 2, then you verify this. So, the statement is true for k in the sense that roots of p2 interlace the roots of p1. So, the first entry d1 is interlaced by the eigenvalues of the leading 2 by 2 matrix d1 e2 e2 d2. Okay. This you verify, that shows that the statement is true for k equal to 1. Next, you assume that the statement is true for k equal to I. Then you denote the roots of pi as alphas, roots of pi plus 1 as betas, and roots of pi plus 2 as gammas. Okay. As you assume the statement to be true for k equal to I, you assume this, that is the betas interlace the alphas, that is the I plus 1 betas will interlace the I alphas, and in the number line you can show the alphas with crosses and betas as bars, and the picture looks like this. Then you need to show that in turn gammas will then interlace the betas, I plus 2 gammas will interlace I plus 1 betas, and that you establish based on this recurrence relation and changes of signs in the roots of the succeeding polynomials. So, rest of the proof I will omit here in the class, but I strongly suggest you that you go through the proof a little carefully. We go rather directly to the procedure. We examine this sequence p0, p1, p2, p3 up to pn for different values of w. For a particular value of w, if we know that the pk and pk plus 1 and pk minus 1 will have their locations of roots in this manner. See, one question we are never raising, that whether the roots are real or not, that question we are never raising, because the matrix is symmetric. So, all the roots are real, that is anyway known, all the eigenvalues are real, that is anyway known. So, if pk has this kind of relationship with pk minus 1 and pk plus 1 their roots, then one thing is very clear. If pk w and pk plus 1 w have opposite signs, then the number of their roots above w can differ by just 1. Why? Because if this sign, that is in this, suppose W falls here, okay, and Pk W has a certain sign, and the at the same W Pk plus 1 has a sign different from that. Okay. That will mean that above that value, above that W, whatever is the number of roots of this, and the number of roots of this can differ at most by 1. Okay. Because at infinity all the Pk's will have plus infinity value, okay, infinity minus something into infinity minus something into infinity minus something, and so on. So, at infinity that polynomial, all of these polynomials will evaluate to plus infinity. So, all of them are positive. So, the moment one root is encountered, the sign changes, okay, for each of them. So, it is impossible that one of them encounters too many roots and the next one has not encountered any root because of this interlacing property. So, Pk and Pk plus 1, two succeeding ones, two continuous ones in this sequence having opposite signs will mean that the higher one has one root more than the lower one above W. Okay. Now, we find that number of roots of Pn above W will be number of sign changes in the sequence from this end to that end, because as many sign changes, if compared to Pn minus 1 does not change sign, that means Pn and Pn minus 1 will have the same number of roots above W, and then from Pn minus 1 to Pn minus 2, if there is a sign change, then we will know that for Pn minus 2 one root less, and so on. So, in this entire sequence the number of sign changes at W will tell us the number of roots of Pn above W. So, P0 has no root. So, number of sign changes will tell you at the end how many roots this guy has above W. Now, if we do this operation at W equal to A and then W equal to B, then above A how many roots Pn has and above B how many roots Pn has. The difference of the two numbers will tell us how many roots Pn has in this interval AB. If at a particular value in this entire examination, in this entire investigation, the Pn turns out to be 0, we know that that value is the root, is a root. Okay. So, after closing like this, that is how many roots in the interval AB, we can consider a plus b by 2 and then see out of those roots in the interval AB, how many are in the lower half A to a plus b by 2 and how many are in the upper half a plus b by 2 to B, and so on. So, like this we can repeatedly use bisection to squeeze each of these roots separately, and then further we can use bisection itself to go on squeezing the interval till we find the root to our required accuracy, or rather than bisection we can find some other equation solving process after locating the roots and separating all the roots. Okay. So, with what interval we start? Do we start from minus infinity to infinity? Then it will be very difficult to process the whole thing because bisection will work indefinitely. There is a little trick in starting the process if you want to solve for all the eigenvalues. Okay. And that tells you this: all the lambda i's, their magnitudes are bounded by this quantity, which is the maximum over all rows of the entries of the rows Ej plus Dj plus Ej plus 1. Take all their magnitudes and whatever is the maximum of the sum over all the rows, no lambda, no eigenvalue of the matrix can have a magnitude which is larger than that. So, if you take the initial interval from minus lambda b and d to lambda b and d, then all the eigenvalues are bound to fall within that, and then you can go on applying bisection in order to separate the roots and separate the eigenvalues, and once you have separated them, then solving for them you can apply either bisection itself or some other equation solving process or root finding process. So, that gives you this algorithm. First, identify the interval a b of interest. Now, interval a b of interest can be either the entire interval minus lambda b and d to lambda b and d if you are interested in finding all the roots, all the eigenvalues, or sometimes your problem may suggest that you are interested in an eigenvalue in a given domain only, in a given interval only. You are not bothered with rest of the eigenvalues which may fall outside this interval. In that case, you take that interval as a b. Otherwise, you take the larger interval in which you are sure that all the eigenvalues will lie. Now, for a degenerate case in which some subdiagonal or superdiagonal entry of the symmetric tridiagonal matrix is 0, you split the given matrix and operate separately with the different blocks. For each of the remaining non-degenerate blocks or matrices, you just do two things. By repeated use of bisection and study of the sequence p lambda, you bracket or separate individual eigenvalues within small subintervals, and then in these bracketed subintervals, by further use of bisection itself or some substitute, some other root finding method within each subinterval, determine the individual eigenvalues. And when the interval becomes extremely small, say the interval size becomes equal to 0.00001, then that means you have actually found the eigenvalue. So, there is no further need to go into that. So, in this lesson, what are the important points that we should keep focus on? First point is that a Householder matrix is symmetric and orthogonal, and it affects a reflection transformation. Second is, a sequence of Householder transformations can be used to convert a given symmetric matrix into symmetric tridiagonal form, and then the eigenvalues of the leading square submatrices form a Sturmian sequence which have interlacing structure in their roots, and this property can be used to separate and bracket eigenvalues, okay, and further solve in a systematic manner. So, we have a little time in hand. So, let us consider a quick example at least halfway, after which you can proceed on that example. Suppose we have got this matrix 2, 3, 2, 5, 4, 3, 5, 7 by 7 matrix. These are the diagonal entries, and the off diagonal entries are 1, 0, 1, 2, 2, 1, right. Subdiagonal entries are also same, and all other entries are 0. So, this is a symmetric tridiagonal matrix possibly obtained after a series of Householder transformations. Okay. So, this is the matrix which we are going to solve for eigenvalues. Now, these two zeros will allow us to split the matrix in this manner. So, this is a 2 by 2 component and this is a 5 by 5 component. This is actually nothing. This you can solve from the eigenvalues of this you can solve from the direct definition itself, because that will involve only the solution of a quadratic. This otherwise would involve the solution of a quintic equation, which is more difficult. So, for this we apply this methodology based on the Sturmian sequence property. So, for that we construct these polynomials. First one is trivial, second one will be lambda minus d1, that is p1. Next, p2 will be lambda minus d2, that is lambda minus 5 into p1 minus E1 square, that is 1. Next, you will have P3, which will be lambda minus D3 into P2 minus E3 square, and what is E3 here? E3 here is 2. So, E3 square into P1, right. Then P4 will be lambda minus D4 into P3 minus E4 square, E4 is 2 into P2. Finally, P5 will be lambda minus D5 into P4 minus E5 square, which is 1 into P3. Okay. So, these things we now try to evaluate for different lambdas to locate the roots of these polynomials. So, for now consider the interval which you need to consider. You would have noticed the intervals as the rows as 1, 5, 2, 2, 4, 2, these are the biggest rows. Okay. So, sum of that turns out to be 8. That means, no eigenvalue of this matrix can have magnitude higher than 8. So, you consider the interval minus 8 to plus 8. So, at lambda equal to minus 8, you try to evaluate this. This is 1 for all of them. This is minus 10. This is minus 8 into minus 5, that is minus 13 into this, that is minus 10 already in hand. Okay. So, what you get? You get minus 13, okay, sorry, minus 5 into minus 10, minus 5 into minus 10, that is plus 50 minus 1. So, you get 49. Okay. Then you come here, minus 8 minus 4, that is minus 12, right, minus 12 into P2, what you have already got, okay, minus 4 into this. So, you will find that this turns out to be positive, then this turns out to be negative, this turns out to be positive, and then you will find that 1, 2, 3, 4, 5 sign changes are there. That will show this. I suggest that you verify and check that these turn out to be positive, negative, positive, and so on. Okay. And then you will find that there are 5 sign changes from top to bottom. That means, above minus 8, P5 will have 5 roots. That means, all the 5 roots are above minus 8. Then you consider the case of lambda equal to 8. This is 1, and as you put 8 here, you will get 8 minus 2, that is 6, positive. Okay. Then you put 8 here, 3 into P1, that is 3 into 6, 18 minus 1. Okay. So, you get 17. Then you come here, 8 minus 4, that is 4, 4 P2, 4 into 17, 68 minus 4 into 6, 68 minus 24. So, you get 44, still positive. Like this, you will find that in this case, all of them turn out to be positive. That will mean, what is the number of roots of P5 above 8, above the value 8? Number of roots is the same as number of sign changes here. No sign change here, so no root above 8. Up to this, we have verified that all the roots are actually above minus 8, 5 roots above minus 8, and no root above plus 8. So, we have verified that bound, that is, all the roots actually lie within minus 8 and 8, right. Now, applying bisection, you try to find out the number of roots above 0, okay, above 0, how many? So, this is 1, as you put 0 here, you get minus 2, as you get put 0 here, you get minus 5 into this, that is plus 10, minus 1, that is plus 9. Then you come here and you find minus 4 into 9, that is minus 36, minus 4 into minus 2, that is minus 36 plus 8. So, minus 28. Like this, as you continue, you will find that this turns out to be positive and this turns out to be negative. That will show the number of sign changes at lambda equal to 0 for these polynomials. This sequence of polynomials is 1, 2, 3, 4, 5. So, all 5 roots above 0. Okay. So, all positive roots. So, this gives you a little further information that all the roots are within the interval 0 to 8. In particular, this is a positive definite matrix, because all eigenvalues are positive. Now, what you will do for bisection? You will evaluate the polynomials, the sequence of polynomials at lambda equal to 4. Okay. So, as you evaluate at lambda equal to 4, you will find that you get 1, 2, and then here minus 2 minus 1, that is minus 3, and then at lambda equal to 4, this is 0, okay, minus 4 into P1, that is minus 8. Then here 1 into minus 8, that is minus 8, minus minus plus 12, that means 4. Finally, here minus 4 minus minus plus 8 is minus 4 plus 8, that is plus 4. So, how many sign changes here? One sign change here, two sign changes here. So, above 4 you will have 2 eigenvalues and below 4 you will have 3. So, you have started bracketing 3 in this interval and 1 in this interval, 3 in this interval and 2 in this interval, right. So, 2 sign changes here at lambda equal to 4, that means above 4 P5 will have 2 roots, 2 sign changes, right. So, in this there will be 2 roots, in this there will be 3 roots. Next, you will go on splitting this. Next, you will evaluate for finding the eigenvalues in this subinterval. You will evaluate at 2 and then possibly at 1 or 3 and so on. Similarly, here like this you go on subdividing the interval till you have separated each of the intervals containing exactly one root of P5, and further continuation in the same process will squeeze the root for you. So, I suggest that you continue this process till you find the eigenvalues with an accuracy of 0.1. That will give you enough practice and you will find that the method works quite comfortably.
There was a small error in the calculation in the board work. So, please note this correction. Here what you saw in the board was this: we were analyzing the eigenvalue problem of this problem, and this is what appeared on the board, and in this there is a correction. This 49 for P2 at lambda equal to minus 8 was not right. The correct calculation shows that it should be 129, the result of which was that the next 3 signs were also mistaken, and the next 3 signs will be this way: minus, plus and minus. And with this, as you will notice that for lambda equal to minus 8 there are 5 sign changes, and that means that all 5 roots are above minus 8, and then for lambda equal to 8 there is no sign change, and that shows that no root is above 8, and in between through bisection then you will evaluate at lambda equal to 0, in which case you will find that all 5 roots are above 0. So, the first 2 columns in this data for lambda equal to minus 8 and lambda equal to 8, you basically get the verification of the bounds of minus 8 and 8 for all the eigenvalues, and the third column lambda equal to for lambda equal to 0 shows that all the 5 eigenvalues are positive, which means the matrix is positive definite. Other than this, everything else is all right in the board work. Thank you.